DOE CSGF Fellow Blake Weatherton in the field of plasma physics at the University of Wisconsin-Madison.
Today, I'll talk about a drift-kinetic method for estimating gradients and plasma properties from single-point measurements. I'll start by talking about what a plasma is and how we model it. Then I will talk about space plasma and spacecraft missions. In particular, I'll focus on magnetic reconnection and the magnetospheric multiscale mission, which NASA launched in 2015 to study reconnection. Then I will talk about the drift-kinetic gradient model and show how we can confirm it with simulation data and what some of the next steps are for the method. So what is a plasma and how do we model it? A plasma is basically a hot ionized gas composed of ions and free electrons. So when you heat up a gas, it starts to ionize, free electrons break off, and you have ions. There can be neutral particles, but we won't consider those here. And when ions and electrons are together, they can interact electromagnetically, and you can have collective interactions with the ions and electrons and electromagnetic fields. So, unlike a typical gas, plasma particles collide with each other less frequently at higher temperatures, which means, among other things, that the electrical conductivity of plasmas is high. So the easiest way to describe this collection of ions and electrons is statistically. Rather than as many individual particles, we see the plasma as distribution functions of these particles, which roughly speaking represents the probability of finding a particle at a particular position and velocity. And this distribution function is governed by the Vlasov-Maxwell system of equations. So ions and electrons have their own distribution functions, and they're governed by that first equation. The zero on the right means it's collisionless, which is a valid form for space plasma for the most part. And then you also have the Maxwell equations in order to govern the electromagnetic fields. So one important thing about plasmas is that there are ways to reduce the model, because a 6-dimension plus time differential equation is an absolute mess to solve. But there are things about plasmas that make them a little easier to solve. So one thing is magnetized plasmas have different dynamics across magnetic fields and along magnetic fields. Because magnetic field will not deflect a particle moving in the direction of the magnetic field, but it will deflect a particle going across the magnetic field such that charged particles will orbit the magnetic field. And that splits the dynamics between parallel and perpendicular directions. So drift kinetics takes advantage of this and integrates the fast motion around the magnetic field out of the equation. And you look at the distributions of the guiding centers. So the guiding center is that point on the magnetic field, essentially, in the drawing, rather than the point that the particle is at any specific time. So we look at the distribution of guiding centers, and we're able to reduce the dimensionality of the equation by 1 by replacing the fast motion around the magnetic field with a conserved quantity, which is the magnetic moment of the particle. You can reduce the model even further to be only in the spatial dimensions, so this integrates all the velocity dimensions out, so you're only dealing with fluid variables. And magnetohydrodynamics is the simplest general model for plasmas. The plasma is treated as a conducting fluid, and you can derive it through a closure of the kinetic equation. So the first equation here is the continuity equation. Then you have a momentum equation and an energy equation. You still have Maxwell's equations, and then this E plus V cross B equals 0 is the ideal Ohm's law that treats the plasma as a perfectly conducting fluid. So when we actually want to solve a kinetic model on a computer, we tend to use the particle and cell method because it includes all the kinetic effects, which can be important for problems like magnetic reconnection. And it goes back to what a plasma is at the core, which is just a collection of charged particles interacting through electromagnetic fields. So each one of these macro particles represents many particles, but it still statistically does a similar thing to the full system. And the general idea is that you look at every particle, you see what the field is at the location of the particle, you advance the particle according to Newton's equations, then you can accumulate currents based on what the new positions and velocities are, and based on those currents, you can use Maxwell's equations to find out what the electromagnetic fields are. So let's talk a little bit about space plasma and spacecraft missions. So first off, magnetic reconnection is a process that changes the magnetic topology where field lines break and reconnect, and I'll play a quick animation of that. Just they come in, they reconnect, and that reconnection actually adds a lot of energy to the system. You convert this magnetic energy into energy in the particles. That can be thermal energy, it can be kinetic energy of non-thermal particles, and also these field lines have tensions and they tend to slingshot the outflows outward. So you can get these really violent events like coronal mass ejections, where big blobs of plasma can be shot off of the sun and potentially towards Earth, where they can interact with Earth's magnetosphere as well. So spacecraft mission will also often consider Earth's magnetosphere or the solar wind that comes from the sun towards the Earth and do measurements in that plasma environment. So in particular, we're looking at reconnection in the magnetosphere. There are two primary locations where that happens, at the day side and in the magnetotail. I'll mostly be looking at stuff at the day side where the solar wind hits Earth's magnetic field, and you can have reconnection there. NASA has this magnetospheric multi-scale mission, and it has a formation of 4 spacecraft in a tetrahedron, and they orbit and look at these reconnection events. So the spacing of the spacecraft allows for some spatial information, but it does not give gradients at the smallest scale. They're still separated by larger scales than you expect the smallest gradients to be, which is somewhat unfortunate. So it would be nice to be able to have more information. And there are a lot of spacecraft missions that don't have the luxury of having 4 satellites measuring things. So if you have just one, it would be nice to know what gradients are like to give you some idea of the context of what you're measuring. And in MMS, we have seen these somewhat interesting observations. So I mentioned before how the dynamics parallel and perpendicular to the magnetic field can decouple in a magnetized plasma. But usually in a magnetized plasma, you don't expect for the 2 perpendicular directions to decouple. But we see that here in this crescent-shaped distribution in the perpendicular velocities, where it's clearly acting differently in the 2 velocity directions. But the interesting thing is the magnetic field is strong enough there that it seems like the distribution should be magnetized. So we were able to come up with this model and confirm it with simulation data. This is a PIC simulation. So you see these distributions on the top that we measure. But if we instead bin the particles by the location of their guiding center, instead of the location of the particles themselves, we actually see these ring distributions, which are gyrotropic. So they don't have any variation in the direction around the magnetic field, which is more what we'd expect for a magnetized distribution. So this is an artifact of a strong gradient at the separatrix. And this kind of ties together the idea of strong gradients being connected with these agyrotropic features in the distribution function. And that's what the model will rely on. So now I'll talk a little bit about what the model does. So the basic idea of the model is that if you have this gradient in the distribution function, you have more particles on the left than there are on the right. But because of the magnetic field, they're coming into the location of the spacecraft from above rather than below on the left. So you expect that this gradient is reflected by more particles coming from the top than come from the bottom. So that's the basic idea and we can figure out what this gradient is based on the difference in the number of particles coming in, essentially. So we can formalize that model a little better in drift kinetics, and these are some of the starting points and how we go through. But the important part is that we eventually get to this model for a gradient and distribution function, which has some information, but it's not necessarily terribly useful. But what does make it useful is we can take moments of this, and the gradient operator commutes with the moment operator. So we can find moments for any, gradients for any moment of the distribution function, which gives us fluid variables, which are much more intuitive as to what we're looking at. So in particular, we like these two moments that are the density and the perpendicular pressure. And these gradient predictions are something that we can fairly easily test with kinetic simulation data. So confirming the model with the simulation data, here are a couple of plots that show what this drift-kinetic gradient method predicts the gradient is versus what the gradient actually is by the finite different method in the simulation domain. So both of them converge to the same thing, although the drift-kinetic distribution is a little bit noisy. So that's encouraging. And a similar thing happens for the pressure gradients. So it looks like the model is working pretty well, though there may be some noise in it. So here's a comparison across a few different simulations we have. So this is different asymmetries in the reconnection. So I hadn't mentioned it, but the reconnection simulations that we ran had one side starting with a higher density of electrons and ions than the other side. So the one we showed was a factor of 1.4 difference in density. We also ran simulations with 7.4 times more particles on one side than the other, and 16. And at the simulation parameters that we chose here, they were all able to reproduce the gradients quite well. So the gradients get stronger in the higher asymmetry runs, and we'd expect our model might have more trouble with that, but it seems to do pretty well at this parameter range, which is encouraging, although there is definitely a fair bit of noise there. So let's talk about a few of the next steps we can take. So we had this scan and density asymmetry that shows that these three simulations all work pretty well. But there are a lot of other parameters, particularly for reconnection, that I can think of that can potentially influence the validity of our model. And it would be good to actually figure out how good the model is over a range of parameters. In particular, the beta parameter, I expect as it goes lower, the model won't do quite as well with the strong gradients, but we haven't been able to test that rigorously yet, and that would be good to know. Then we can also potentially introduce higher order corrections into the theory to see, I guess, to better understand how well things work as well. And then there's the obvious thing of applying it to MMS data. You can compare the gradient predictions of each spacecraft to the gradient you'd predict from having the 4 different measurements of MMS. And you can also potentially, if you have 4 local gradients, you can maybe try to reconstruct the reconnection geometry a little more explicitly. So there are some interesting things that can be done that we haven't done yet. At this point, I'd like to say thanks to Krell and the CSGF for making grad school a lot easier for me. And I would also like to thank my collaborators on this work. At this point, I can take questions.